So in this lesson, it's 1.2, we're going to look at the slope of a tangent. Right, now, for the slope of a tangent, right, so here we have a curve, this blue curve here. A tangent, if you pick any point on that curve, a tangent is a line that best represents how steep the curve is at that point. Right? Now, before in earlier probably math courses, definitely physics courses, you sort of just estimated a tangent, and you did this, found the slope of the tangent using rise over run, or y2 minus y1 over x2 minus x1. What we're going to do today is we're going to look at, for example, take a look at this curve here. Here we have a point P. Our goal is to figure out the slope of the tangent at point P. We're going to try to do a little bit more of an accurate way as opposed to trying to estimate what the tangent would look like and finding its slope. Instead, we're going to look at the secant. So if we choose a point Q here, notice the slope of PQ is like so. But if I choose a Q closer to P, the slope gets closer to being the same as this tangent. And if I just keep making Q closer and closer and closer, we get closer and closer and closer. So let's investigate that with some numbers. Down here, we have some numbers. Down here we have some numbers. And what we're going to do is, for the graph y equals x squared, so not this one here, but I mean just flip it, y equals x squared, first we're going to find the value of y as the value of x gets closer and closer and closer and closer to P, because our point P here is going to be 3 and 9. So if we do that, first 3.5, well, y is simply 3.5 squared, which is 12.25. I'm going to zoom in a little bit here so it's easy to write. There we go. 3.1, well, 3.1 squared is 9.61. 3.01 squared, now we're going to keep all the numbers on a calculator, try and be as accurate as possible without any round off error. And similarly, 3.001 squared gives us our y coordinate on the graph y equals x squared is 9.006001. Now what we're going to do, knowing point P as 3, 9, I'm going to find the slope of the secant PQ. First I'll do PQ1, then PQ2, and PQ3, as PQ gets closer and closer and closer to being the slope of that tangent at P. So let's start with over here. We're just going to use the equation y2 minus y1 over x2 minus x1. So for Q1, so PQ1, the slope at PQ1 would be 12 minus 12.25 minus 9 all over 3.5 minus 3. And we're going to get 6.5. You can do that again for Q2. So this one was PQ1, slope of the secant. For PQ2, our slope will be, so rise, so 9.6, so the difference in our y coordinates, 9.61 minus 9 over the difference in our x coordinates, which would be 3.1 and 3. And we get 6.1. And we can continue doing that for PQ3. And if we did it there, we would get 6.01. And you can test this for yourself as well. And if we did the same thing for PQ4, you would get 6.001. So it looks like the slope of these secants, as q gets closer and closer and closer to p, those slopes are getting closer and closer and closer to 6. Let's look at this from a different point of view. From a different point of view, I mean we're going to take q's not to the right of p, but to the left of p. So instead of going from a number bigger than 3, like 3.5, and going closer and closer and closer to 3, we're going to do a number less than 3, like 2.5, and get closer and closer and closer and closer to 3. So if you do that, first you need to find the y-coordinate. So 2.5 squared, since our graph is still y equals x squared. That's the graph we're analyzing. So our y-coordinate then, at the x-coordinate 2.5, would be 6.25. 2.9 squared would be 8.41. 2.99, again, keep all the digits on your calculator, 8.9401. And 2.999 squared would be 8.994001. And then we do the same thing. Find the slope of these secants to see as it gets closer, as q gets closer and closer to p. So pq5 then would be 9 minus 6.25 all over 3 minus 2.5. So rise over run, difference in our y-coordinates, y2 minus y1, difference in our x-coordinates, x2 minus x1. And we get 5.5. Okay. I won't do this each and every time because I think we know how to find the slopes of secants, but definitely try it yourself and you'll see that PQ6, or the slope for PQ6, is 5.9. PQ7, 5.99. You can probably see where this is going. PQ8, 5.999. So again, whether we're taking secants coming from the right of point P or from the left of point P, as they get closer and closer and closer and closer to point P, it looks like our slope is getting closer and closer and closer and closer and closer to 6. So as you can see what we're doing, we're trying to find the limit of those secants as Q gets closer and closer and closer to P. So instead of having Q, say, 1 unit away from P, or half a unit away from P, or 0.1 or 0.00001 unit away from P, we'll just say it is a value h away from P on our x-axis. So that means if we're going to take the point P, which is 3,9, and we're going to take a generic point Q as that 3 plus a little tiny bit, just a little tiny bit, and therefore our y-coordinate for our graph y equals x squared would be that x value, 3 plus that little tiny bit of h squared. So this is what our Q is going to be. And what we're going to do is apply our slope formula. Okay, a change in y over the change in x. Right, so your slope is simply change in y over our change in x. Now our change in y is going to be this 3.h squared. So 3 plus h squared minus, so that's y2 minus y1, which is for p, so 9, all over x2, which is 3.h, or 3, why do I keep saying 0.3 plus h, minus x1, which is just 3. So notice on the denominator we have 3 minus 3, so that's nice, that can go already. Now, what we're going to do is to figure out exactly what that slope is. I'm going to introduce some new terminology here. I'm going to write it as a limit where h gets closer and closer and closer to being 0. So that's what that terminology means. Lim stands for limit, as some variable, in our case h, gets closer and closer to 0. Because that's what we want. We want q to get closer and closer and closer to p, right to the point where it's almost right on p. So the smallest number you can think of, right? But not quite 0, but approaches 0. Now, if we simply sub in h equals to 0 into this equation, we have a huge problem. You can probably see that on the denominator there. You're going to end up dividing by 0. But let's play with it a little bit here. Okay? So this is our slope equals the limit as h approaches 0. So let me expand the numerator here, the square. So that's just a perfect squared, so we're going to get 9 plus 6h plus h squared, and then I still have this minus 9 over there. You might be able to see what's going to happen. 9 minus 9, goodbye. Okay. Let me just continue over there because I reached the bottom of my page. So now the slope equals the limit as h approaches 0. On the numerator, I have 6h and h squared, so I'm going to factor out an h, which will give me 6 plus h over h. So h cancels. And now we have the limit as h approaches 0 of 6 plus h. So as h approaches 0, that just equals 6. And like magic, we have the slope of that tangent. So if we look at our graph then, and I have a nice graph here, you can see at the point 39, which would be over here, all the way up there, right? The slope of that tangent is 6. And if you want, and I recommend you can draw secants on it, just like we did up here, and see that that slope, whether it's coming from the right or from the left, and we'll talk about limits in our next lesson coming from the right and left, or the one after that, somewhere in this chapter, okay? And how they will sort of converge to a certain value. Now we can write this as an equation. So I have this equation up here. So initially I wrote the limit is delta y over delta x, and essentially in this case you're pretty much taking that delta x between p and q and reducing it down to 0, as close as you can to 0 anyways. Right? It's different from saying it equals 0, reducing it as close as you can to 0. Right? And that's going to be the limit, right, of some function. In our case we did an example of x squared, but you're not doing the function at x, you're doing the function at whatever value of p you're looking at, which would be a, plus that little bit of h. Right? So that's your y coordinate, your y coordinate for your point q, if you like, minus your function at a, which would be your y coordinate for point p, all divided by h. And h is your change in x. As you noticed before, you simply get a plus h minus a. So the a is canceling, you're just left with h on the bottom. So we're going to use this limit equation called the limit of the difference quotient. Difference meaning your slope, differences between y2 and y1, x2 and x1, and quotient meaning one over the other. Okay, and we're going to do some sample problems. Let's zoom in a bit here to our first example. So first example says, using the definition of the slope of a tangent as a limit, determine the slope of the tangent to the curve. Oh, it's not x squared anymore. It's minus x squared plus 4x plus 1 at the point determined by x equals 3. All right. So if x equals 3, right, that will be a. Right? in our equation. So just as a reminder, our slope is written as the limit as h approaches 0 for the function at that value a, whatever point you're looking at, plus h, minus that function at a, all divided by h. Okay, so let's look at what each of these are. Well, we know what h is, but let's just separately look at what is f at a plus h. So what we're doing is, it says y equals, but if you like, we're going to start using function notation now. Right, so this function at x is this polynomial. But I'm going to replace x with a plus h. So that's going to give us minus 3 plus h squared plus 4 times 3 plus h, and then plus 1. Then we're going to have to expand and simplify this. Here we have a nice perfect squared, so minus we have h squared plus 6h plus 9. Right, here we have plus 12 plus 4h, and that plus 1 at the end. So collecting like terms and simplifying a bit, we'll end up with minus h squared minus 2h plus 4. All right, so that's the function at a plus h. Now the function at just a, which has a value of 3, right, is just, well, if you want, you can write 3, because I could have written up here 3 plus h, because the question says a is 3. Now you just substitute 3 into our function here. So we get minus 3 squared plus 4 times 3 plus 1, which gives you minus 9 plus 12 plus 1, which is 4. Now let's plug this into our equation here. So m, you scroll down a bit here. I don't have much space. All right. M equals the slope is the limit as h approaches 0 for f at a plus h, which is minus h squared minus 2h plus 4, and then minus f at a, and f at a is 4 for f at 3, so minus 4. That looks good already. All over h. So our 4's cancel, and you might be able to see where I'm going with this, but I'm going to factor out an h. So this is the limit. Yes, you have to write this every time. Is going to be h times minus h minus 2 over h, so our h is canceled. And now as h approaches 0, we're left with negative 2. So there is the slope at that point x equals 3. Now part 2 says determine the equation of that tangent. Well, the tangent is a line, so we have to determine the equation of the line. So to find the equation of that tangent, well, again, the equation of a line, we know that the point that we're looking for is at x equals 3. So at x equals 3, and we know when we plug in x equals 3 into the function, we get 4. So our y-coordinate is 4. So at the point 3, 4, we know the slope is negative 2. Now we can just use our equation for the slope from grade 9, where we have y minus y2, which is unknown, any y, minus y1, which is a point that we know, sorry, over here, 4, so y minus 4, over any other point on the line x minus our point p, 3. That will always be negative 2, because it's a line. That's the slope of our line. So now we just rearrange this, so that gives us y minus 4 equals negative 2 times x minus 3. Right? We can expand that, bring the 4 over, and we'll get y equals minus 2x plus 10. So there's the equation of. So the next example, same thing. We're going to analyze a different function and find out what the slope of the tangent is at that function by using this difference quotient, by taking the limit. So let's do this example over here. So we have a function f at x is 3x plus 6 over x. So let me write our equation. So the slope m equals the limit as h approaches 0 of this function f at, now the x-coordinate is 2, but we're going to add that little bit of h, and then we're going to minus that function at 2. All divided by h. So let's see if we can do this. So the limit as h approaches 0. So let's substitute 2 plus h into our function here. So we have 3 times 2 plus h, and then plus 6, all over x, which is again 2 plus h, minus that function at 2, okay, which would be, well, we actually don't need to solve it because it says right here in the question, at 2, the function equals 6. But you can substitute 2 in there to confirm that it does equal 6. But I'm just going to write minus 6. All over, oh, I know a fraction within a fraction. What are we doing? H. Alright, so we need to play with this again because we can't set h equal to 0 right now and hope everything works out because we'll be dividing by 0. That's not good. Okay. So let's start by expanding a bit here. So I'm going to FOIL this up here. We're going to have the limit as h approaches 0 of 6 plus 3h, and then we still have this plus 6 over here, all over 2 plus h. And what I'm going to do is this 6, I'm going to turn it into a fraction which has the same denominator. So to do that, I'll have to multiply the numerator by the same thing. So I'm going to have 6 times 2 plus h, all over 2 plus h. And all of that is all over h. We're having fun now, aren't we? All right, let's continue working with this. So the limit as h approaches 0 then. So now I can subtract these numbers. Right? So here I have 6 plus 6, which is 12, minus, and 6 times 2 is 12. Awesome. Those are all going to just disappear for me. And I'm going to be left with, here we have 3h minus 6h. So I'm left with negative 3h. And that is all over 2 plus h. But since these are both in the same denominator, it's now one fraction. If I write 2 plus h here, I can keep that on the denominator with this h. So I have h here. Much nicer. See? Goodbye h. So now, if we set h to approach 0, the limit of this function is minus 3 over 2. Therefore, slope of the tangent for that function at that 0.26 is minus 1.5. It says find the slope of the tangent to f at x, where the function is the square root of x, when x is 9. Well, when x is 9, you can see what your point is. Right? Your point is 9 and the square root of 9 is 3. So find the slope to the tangent at f at x equals the root of x at the point 9 and 3. So let me grab some space over here so we can do this. I'll use a different color. Alright, so the slope is the limit. You guys are going to love that word. Of h as it approaches 0 for our function at a plus h minus that function at a all over h. And you're going to use that equation so much you're going to have it memorized without even trying to memorize it. Alright, so this is for our function that we're working with, the square root of x. as h approaches 0, this is going to be the function of a plus h, so the square root of x, which was 9, or the value of a, 9, plus that little bit of h, minus the square root of 9, which is 3, all over h. Now you're thinking, what are we going to do here? Well, remember yesterday when we did rationalizing denominators, and I did that one example where I said sometimes it's useful to rationalize the numerator. This is the example. So this is where it becomes useful to do that. So let's do that. Let's multiply top and bottom by the conjugate of the numerator, which is going to be the root of 9 plus h plus 3, all over the root of 9 plus h plus 3. So that's going to give us the limit as h approaches 0. So here we have our difference of squares, so we're going to end up with 9 plus h minus 3 squared, which is 9. Alright, those 9s are going to go all over h times by the root of 9 plus h plus 3. Alright, these 9s will disappear, and then we're left with just h on the numerator. And so that will disappear as well, leaving us with just 1 on the numerator. So now we have the limit as h approaches 0 of 1. I'm going to just rewrite this. 1 over the root of 9 plus h minus 3. As h approaches 0, this is just the square root of 9. This should say plus 3. Square root of 9. Square root of 9 is 3. 3 plus 3 is 6. So we get 1/6. So the slope of the tangent of the function root of x at the point 9 and 3